Hello, I'm Vasileios Vasilopoulos and I'm going to present you the work Reactive Semantic Planning in Unexplored Semantic Environments using deep perceptual feedback done with my colleagues at the GRASP Lab. Motion planning is a popular subject in robotics and there exists a rich body of work in the field. For example, prior work has focused on sampling-based techniques such as the RRT star shown here that require no explicit description of the configuration space and can also guarantee probabilistic optimality when facing a known environment. However, sampling-based methods suffer from narrow passage problems, and in the presence of unknown environments they require constant replanning that usually comes with no convergence guarantees. More recently, deep learning methods have gained significant attention since they require no environment or robot model for navigation. However, deep learning algorithms are known to suffer from overfitting problems to the specific environments used in training and also come with no collision avoidance or target convergence guarantees. Instead, this work focuses on reactive vector field-based methods that provide obstacle avoidance and convergence guarantees, while at the same time solving the kinodynamic problem of finding appropriate inputs to the robot. Despite their advantages, these methods usually require significant offline tuning of potential functions, or are limited to simple unknown environments with only convex obstacles. Our work provides solutions that address these two problems. Focusing on past work in reactive planning, navigation functions solve the problem of navigating to a desired target from almost any point in the configuration space in a priori known environments. On the other hand, recently developed doubly reactive algorithms, where both the trajectory and the vector are generated online, work well in unknown but convex environments. This work combines the two approaches to solve the navigation problem in geometrically complicated, unknown environments. More specifically, we assume that the robot possesses a sensor of fixed range capable of recognizing familiar objects as well as measuring range to nearby obstacles. For our experiments, this sensor is realized with a combination of a LiDAR and an RGB camera. We also assume that any non-convex obstacle in the environment is familiar in the sense of having a recognizable polygonal geometry, and all unknown convex obstacles are well separated from all other obstacles in the environment. Apart from these assumptions, all obstacles are initially unknown and discovered online during execution time. The goal is then to find a controller that probably guides the robot to a possibly moving target while avoiding all obstacles in the environment. The fundamental idea of our reactive controller is to construct increasingly simple but topologically equivalent environments, find a map that is a diffeomorphism from the original environment to a model environment where all obstacles are convex, apply a doubly reactive navigation strategy in the model environment, and finally pull back the resulting vector field to the original environment. More specifically, except for the physical space that the robot discovers as it navigates to its goal, we also use the semantic space, that includes all recognized familiar obstacles and the observable portions of unknown obstacles, the mapped space, where all overlapping obstacles in the semantic space are consolidated in real time, and finally, through a series of intermediate spaces, the model space, where all mapped space obstacles are either transformed to disks or merged to the workspace boundary to form a convex environment. The main focus is then to find a map H between the mapped and the model space. In order to do this, we rely on prior work on the transformation of star-shaped obstacles. For such obstacles, based on smooth but non-analytic functions, we construct smooth switches that vary between 0 away from the obstacle and 1 on the obstacle boundary, as well as deforming factors that map the boundary of the obstacle to that of a topologically equivalent disk. We then combine the smooth switches and the deforming factors to form the map H between the free space in the mapped space and the free space in the model space, and then show that this map is a C-infinity diffeomorphism. Also, with the use of smooth switches that limit the effect of the diffeomorphism to a neighborhood of each obstacle, no unknown obstacles are used in the construction. In another work, we extend this construction further for arbitrary planar obstacles. So, given a specific non-convex obstacle, we first perform triangulation and build a connectivity tree based on the dual graph of this triangulation. Then, the goal becomes to successively purge each leaf of that tree. First, we find an anchor point in the leaf's parent, and we identify two polygonal colors, one for the leaf itself and one that defines a neighborhood around it. For each of these colors, we construct implicit functions that define them, using the R-function methodology from the field of computational geometry. Using these functions, we construct a smooth switch that varies between 0 on the boundary of the external polygonal color and 1 on the boundary of the leaf itself. We also construct deforming factors that map either the boundary of the leaf to the boundary of its parent, or the boundary of the root of the tree to the boundary of an equivalent disk. We can then write down the map between the mapped and the model space for each leaf purging, as described above for the case of star-shaped obstacles. If the obstacle intersects the workspace boundary, we simply merge it there, by treating the root of the tree as an additional leaf that needs to be merged. This work extends this construction by replacing the computationally expensive triangulation with convex decomposition. More specifically, we show that the same construction can be streamlined by using any convex decomposition method that does not introduce additional points except for the polygon vertices. Here we employ the Green's algorithm as an efficient method for convex decomposition in polynomial time. As the root convex polygon, we pick either the polygon with the largest area if the obstacle needs to be deformed to a disk, or any polygon adjacent to the workspace boundary if the obstacle needs to be merged to this boundary. Here are some examples that demonstrate how the method works. With convex decomposition and by successively performing leaf purging as described before, any non-convex obstacle can be eventually mapped to an equivalent disk, no matter how many non-convex fingers it has. The efficient implementation of our leaf purging algorithm in C++ also allows for real-time performance on robot hardware. A reactive controller for fully actuated particles is the push forward of a doubly reactive navigation strategy in the model space through the inverse of the constructed diffeomorphism. Our navigation strategy in the model space is to just follow the projection of the goal yd onto a local free space around the robot position y, constructed as the intersection of separating hyperplanes, one for each familiar obstacle deformed to a disk, and for each segment of an unknown convex obstacle, as shown in the figure. Here, y is the position of the robot in the model space, and yd is the position of the goal in the model space. To formally prove target convergence in a changing semantic world, we employ a hybrid systems formulation, where each mode is defined by the subset of already localized familiar obstacles. The controller in each mode is the push forward of the doubly reactive navigation strategy through the inverse of the diffeomorphism for the given subset of localized familiar obstacles. The guards describe the perceptual updates where a previously unexplored obstacle is discovered, and the resets are just the identity in the physical space with possibly discrete jumps in the model space. Here we include an example where the robot starts navigating to a predefined target in an unexplored environment, successively localizes familiar obstacles, and explores the nodes and edges of the corresponding navigational hybrid systems graph. In this work, we also extend our formal guarantees to moving targets such as humans. We assume that the target is friendly in the sense that its model space velocity is such that the target either approaches the robot or slows down when the robot gets close to obstacles or when the robot gets too close to the target itself. With these conservative assumptions, we can guarantee that the distance of the robot to the target in each mode of the hybrid system will never increase. Overall, this work presents a variety of formal guarantees. First, we show that the constructed map between the mapped and the model space is a C-infinity diffeomorphism away from sharp corners. Also, the reactive controller in each mode of the navigational hybrid system now guarantees collision avoidance and convergence to the designated target except for a set of measure 0. The overall hybrid reactive controller is also a well-behaved hybrid system in the sense of being deterministic, non-blocking, and having a unique execution, and also guarantees collision avoidance, generates a piecewise smooth flow, and always steers the robot to its designated target. Finally, we can guarantee tracking of moving non-adversarial targets given some sufficient conditions on their behavior. Simulation results demonstrate the validity of our approach in a changing semantic world cluttered with both familiar obstacles, whose pose is initially unknown, and completely unknown convex obstacles. Notice how familiar obstacles appear in the semantic space and are subsequently consolidated in the mapped space, and how fragments of convex obstacles appear and disappear in both the semantic and the mapped space. Consolidated obstacles in the mapped space are then either transformed to disks or merged to the workspace boundary, affording direct implementation of the doubly reactive navigation strategy for convex environments. We also compare our approach with a dynamic replanning algorithm RTX designed for unknown environments. As anticipated, in the presence of narrow passages, RTX requires an exponentially large number of samples to find the solution. On the contrary, our algorithm always guarantees safe passage to the goal. For our experiments, we leveraged existing technology on object pose estimation using deep learning to detect semantic key points on a 2D image, and couple it with a semantic SLAM algorithm that keeps track of both the robot and the encountered objects in the environment by building a 3D semantic map. Except for obstacle identification and robot localization, the semantic mapping module makes the SLAM problem solution more robust by localizing against semantic instead of just geometric landmarks, and also affords semantic planning by using these semantic landmarks to design more complex robot missions. Our experimental setup consists of our perceptual pipeline, using 3 different neural networks for object and human detection, object key point estimation, and human mesh extraction, our semantic mapping module that fuses information from the perceptual pipeline to build the semantic space, our mapped space recovery module that consolidates obstacles in the semantic space to form the mapped space, and finally our reactive controller, which uses the mapped space information to design the control policy and update the robot inputs. Our controller is implemented in Boost using C++ and communicates with the robot using ROS. All algorithms are implemented on board an NVIDIA Jetson Xavier GPU unit, with the control update at 30 Hz and the perceptual updates at roughly 4 Hz. In the first set of experiments, we considered tracking of a static or moving target. Here, the robot is commanded to navigate to a predefined goal location, shown as a purple dot in the semantic map at the top right. Notice how the robot detects objects and geometric features in the bottom first-person view screens, localizes obstacles in the semantic map in real time, and successfully avoids them. In the second experimental run, we command the robot to move to the same predefined location unless it sees a human. In that case, it is commanded to follow the human while avoiding obstacles. The increasing robustness of our modular approach allows us to repeat the same experiment in several different obstacle configurations, as well as different environments, without retraining our perceptual networks or modifying the navigation strategy. We can also use the same strategy on a different robotic platform. Here, the Ghost Spirit is capable of following a human while avoiding familiar and unknown obstacles in different configurations, environments, and lighting conditions, indoors and outdoors. In the second set of experiments, we use the semantic feedback and human mesh extraction capabilities to perform experiments with predefined logic. Here, the robot is commanded to move to a predefined goal location unless it localizes a cart. In that case, it is tasked with moving to an obstacle-free side of the cart and face it. Here, the robot follows the human until it recognizes a stop signal as a raised hand. It then autonomously navigates back to its starting position. Here, the robot stays in place until it sees a human falling down. It then avoids the obstacles to approach that human. In summary, this work presents a reactive controller with provable guarantees of collision avoidance and tracking of fixed and non-adversarial moving targets in unexplored semantic environments. The reactive planning architecture from prior work is streamlined and accelerated with the use of convex decomposition for familiar obstacles, while the integration of reactive planning, semantic SLAM, and human mesh extraction affords semantic planning in various unknown environments. Our tools for both the MATLAB-based simulation environment and the reactive controller in C++ and Python have been released on GitHub. Thank you for your attention.